As a kid, comic books and sci-fi movies made me believe that radiation made superheroes. It was always a story of a regular human getting exposed to something radioactive and then they would develop superpowers. But what exactly is radioactivity? Well, it has something to do with atoms and energy. To actually understand it, we need to first understand a little bit about the structure of an atom. So an atom is made of tiny particles called electrons, protons, and neutrons. Neutrons and protons are inside a small spherical region at the center of an atom called the nucleus. Meanwhile, the electrons revolve around this nucleus. Okay, now that we know a little bit about the basic structure of an atom, let's get to what it has to do with radioactivity. There is a lot of energy within the nuclei of atoms, and sometimes the nucleus of the atom itself is very unstable. So much so that the nucleus needs to release energy to become stable. This release of energy is what we know of as radioactivity. Now that we know what radiation is, let's move on to how it's connected to our world. You might be surprised to know that radioactivity is actually all around us. It's happening everywhere. It's happening in the rocks below our feet, at the center of our planet, and even within the sun. There are small amounts of radioactive materials in the air and the water, and even in the food supply. Wait, does that mean we're potentially harming ourselves? No, there's no need to be alarmed. It's fine, I promise. I'll tell you what I mean. For example, bananas have naturally high levels of potassium, and a small fraction of all potassium atoms are radioactive. But it is a very small amount of radiation. To put that into context, you would have to eat about 100 bananas each day to receive the same amount of radiation exposure as you get each day in the United States from natural radiation in the environment. Humans produce radioactive material for nuclear power and nuclear weapons. We've also used the science behind radioactive decay to learn more about the ages of the things in our world. So how exactly do we determine the age of something using radioactivity? Well, we can measure the amount of radioactive atoms and the amount of atoms formed due to radioactive decay and use this to help us determine how long it's been since the material was formed. There are several different ways to do that. Some of the most popular ones are potassium-argon dating, uranium-lead dating, and carbon dating. Some techniques are preferred for dating younger items, such as Paleolithic cave paintings and human artifacts, and some for dating older items, such as meteorites and moon rocks. Ages work a little differently with these things, as you can see. Different methods of radiometric dating are only accurate for different lengths of time and only work on certain materials. You'll see why shortly. For now, let's focus on the carbon dating method. It starts all the way up in our atmosphere. Every element has isotopes or variants with different numbers of neutrons in the nucleus. And carbon-14 is one such isotope of carbon that is continually being formed in the upper atmosphere from the reaction of nitrogen with cosmic rays. When C14 reacts with oxygen, carbon dioxide is formed. Since all living organisms take in carbon dioxide, this way plants and animals take up carbon-14 from the atmosphere. When they die, they stop absorbing it and their carbon-14 content starts to decrease at a rate determined by the law of radioactive decay. So what is this law? This law states that the rate of decay of radioactive atoms at any instant is proportional to the number of atoms present at that instant. The time taken during which half the number of atoms present initially in the sample of the element will most likely decay is called the half-life of the element. Confused? Don't worry. Let's look at an example. We'll say our radioactive atom in this case is a marble that has the half-life of exactly 1 hour. So let's say the time right now is 7 a.m. and you have 100 marbles. After 1 hour at 8, according to the law of radioactive decay, you have half the number that you had in the last hour. So now you're down to 50 marbles at 8 a.m. After another hour at 9, you have half the number of marbles you had at 8. So now you're down to 25 marbles. So if you follow this pattern, how many marbles would you have at, say, 12? Well, at 10 you'd have half of 25, is 12.5. At 11 you'd have half of 12.5, which would be 6.25. And so at 12 you would have half of that value, giving you 3.125 marbles. So if we were to represent this by showing the number of marbles we have at a given time, it would look somewhat like this. As per the law, the change in number of marbles per hour is directly proportional to the number of marbles left after 1 hour, and that is exactly what's observed here. Here, your half-life is an hour, and so, for every hour, the number of marbles you have are reduced by half. If you want to know how long you've had those marbles, all you would need to know is how many marbles you started with and the half-life of each marble. This is basically how the radiocarbon age of a certain sample of an unknown age can be determined. By measuring the number of active C14 atoms left, you can find out the age of the decayed organism. However, because the half-life of carbon is only 5,730 years old, the concentration of carbon-14 in a body after, say, 50,000 years is far too low, and so it often cannot be used to irradiate items older than that. Uranium lead dating, on the other hand, can be used to date items from 1 million years ago to over 4.5 billion years ago. And potassium argon dating can be used for items more than 100,000 years old. So the next time you hear a news story about an ancient archaeological discovery, see if scientists use any radioactive dating methods to study it, now that you know how it works. Oh, and here's a cool fact to leave you with. So without the radioactive decay of elements in our planet, like uranium-235, uranium-238, potassium-45, and thorium-232, the Earth would have frozen over and become a dead world a long time ago.